Hello, my name is Ognjen Marjanovic and I'm a senior lecturer in the School of Electrical and Electronic Engineering at the University of Manchester. We will start this mini lecture by looking at the fundamental relation that underpins the transient behavior of the systems. Power is equal to rate of change of energy. This type of equations is called differential equation because it involves differentiation term and simply says that power is equal to rate of change of energy. And this type of equations tells us that if we want to have instantaneous change of energy, we need infinite power, which is not possible in the real world. And that is the very reason why we have transient behavior in general systems. Now, this is true for any kind of system, mechanical, electrical, or thermal. And we will, in this mini lecture, derive equations that govern their transient behavior, starting from this fundamental relation. Let us start with a simple example of a car that is moving from standstill to a certain speed and derive the equations that describe its motion. And we start with the energy equation. So energy, kinetic energy of a car, is equal to mass times the velocity squared divided by 2. Now, what we need to do now is differentiate the energy in order to get the power. So we can do dE by dt, which is equal to mass, which is constant and doesn't get differentiated by time, mass multiplied by d by dt of v squared over 2. So d by dt is equal to mass times, now when we differentiate this term here, we actually get v times dv by dt. And this is really it, because here what we now realize is that we actually have the force equation. Mass times acceleration is giving us force, and force times velocity is power. So we know now that force is equal to mass times the rate of change of velocity. This is a well-known Newton's second law of motion, okay? But it might not have been presented to you before as a differential equation rather than as an algebraic equation, force equals to mass times acceleration. But here now you have the equation expressed in a differential equation form, which describes, for example, in this case, that the car's velocity cannot change instantaneously unless we have an infinite force applied to it. Let us look at another example, which is filling up a glass of water up to a certain height. This particular example of a mechanical system is in fact extremely useful when trying to understand transient behavior of an electric capacitor. So we're going to derive equation for the glass filling up with water. So we have a glass. We have an inflow of liquid, the rate of inflow. Then we also have in the glass cross-sectional area of the glass, which we call C, and also the height of the liquid inside glass, which we're going to actually note as V, which is not really intuitive and probably the only piece of dodgy nomenclature so in this mini lecture, but it will become obvious later on why we have that. So here what we have is also the amount of liquid inside, like the volume. So we want to give the expression relating amount of liquid and the flow, inflow I. And actually this is given by differential equation because the rate of change of the amount of liquid in a glass is actually equal to the inflow. It's actually equal to inflow minus the outflow, but we are not having any outflow of this glass. We're simply just taking the water into the glass. So the rate of change of the amount of water is given by the inflow. But also we know that the amount of liquid is equal to cross-sectional area multiplied by the height of the liquid. This is the amount of liquid. Cross-sectional area times the height of the liquid in a glass. So if we combine these two equations, we will actually get something that looks like this. here it is. We can take C out of this differentiation because the cross-sectional area is not dependent on time. And we have differential of the height. I is equal to C times rate of change of height. The inflow is equal to cross-sectional area times the rate of change of height. This equation relates now the inflow of liquid and the height of the liquid inside the glass. But we'll find this equation actually looks identical to one of our electrical system equations that we'll cover shortly. So how does this actually relate to a capacitor? Well, actually, in the case of a capacitor, we again have inflow, not this time of water, but of charge. And we have equivalent of a volume, which is actually the amount of charge deposited on the plates of the capacitor. So again, we have I, but this time it's a current. And our new A, which used to be the amount of water, is the amount of charge on the capacitor plates. And guess what? C turns out to be a capacitance in the case of the capacitor, whilst V turns out to be voltage across the plates of the capacitor. So therefore, the relationship between a current and the rate of change of voltage across the plates of the capacitor is also given by this very same equation here. This was the reason why previously we introduced V for height instead of H, because we wanted to make you see how the equations are actually absolutely identical. The current is equal to capacitance times the rate of change of the voltage across the plates of the capacitor. So if we observe this equation a little bit more closely, we can see that, for example, the greater is the current of charge coming into the plates of the capacitor, the greater will be rate of change of the voltage across the plates of the capacitor. And very similar kind of behavior we have in a case of the glass being filled with water. The bigger is the inflow of liquid into the glass, the faster is the height of the liquid changing. And in case of the thermal systems, guess what? We have exactly the same thing again. So the equation in that case looks slightly different. And it's given as so what we have here is the heat inflow is equal to thermal capacity. Surprise, surprise, the term looks very similar to the capacitance. Capacity times the rate of change of temperature. So instead of having voltage here, in case of the electrical system, for the thermal system we have temperature, and in case of mechanical system we either had the height of the liquid or the velocity of the car. And here we have a capacity, thermal capacity. Here we have capacitance or the cross-sectional area in case of the glass, or we had the mass in case of a car. And on this side, here we have a heat inflow, here we have a current, here we have the inflow of liquid, and in case of the mechanical cars example, we had force. So there is a huge correspondence between these seemingly dissimilar systems through these equations, differential equations. So far, we have assumed that the inflow of liquid into a glass or a charging current into a capacitor or the heat flow into the heated object remains the same as the time goes by. If this was the case, then the rise of liquid in a glass or the voltage across the plates of a capacitor or the temperature of a heated object would just increase at a steady pace as time goes by. Obviously, this is not the case in real life. In the case of a liquid, it will overspill when reaching the top of the glass. In the case of a balloon, the membrane will collapse eventually. In the case of electric capacitor, voltage buildup across the plates of the capacitor will cause the electric separation to collapse catastrophically. So far, we have looked at the equations like this one. Force equals mass times the rate of change of velocity. And also the one in the case of the capacitor, which was current is equal to capacitance times the rate of change of voltage. So these equations, differential equations, a very similar form. In both cases, we are sort of implicitly assuming that force or the current is constant, and that would result in a constant rate of change of either velocity or the voltage. In reality, this is not really the case. Very often we will find that the resultant force acting on a mechanical object or the current flowing into the capacitor is actually dependent on either the velocity or the voltage, respectively. And we will first look at the mechanical system to demonstrate this point. And the mechanical system in question is a person who's just been thrown out of the airplane with or without parachute. It doesn't matter, equations still stay the same. So in this case, we will look at this equation, but we will now think about what is the resultant force that's acting on the person that jumps out of the airplane. Now this force is actually composed of two force components. One of them is a gravitational pull, capital letter G. This is the gravitational pull equals to the mass times the gravitational constant, small g. But also, there is a frictional component acting on our body, falling down. And this one is acting in the opposite direction to the gravitational pull. We will denote the frictional component as capital B. Whilst we assume that the gravitational pull, G, is constant, the frictional component is actually dependent on the velocity. And very often we model this as B equal small b, which is the frictional constant, times the velocity v. So now we have the equation, which is F, force, which is equal to mass times the rate of change of velocity, which is equal to G minus the frictional term, B times V. So now we have an expression, and we can get rid of this part, which is showing us how the velocity of the object or a person falling down from the airplane is changing. And we notice that this time now, unlike here where the left-hand side, the force was constant, here the force has a constant component G, but also the component that depends on the velocity, the frictional component. As soon as the person is dropped out of the plane, their velocity increases at the rate given by the gravitational constant G, 9.81 meters per second squared. Does their speed keep increasing at a steady rate as we go through time? Initially, yes, but not forever. Why? Because as the velocity builds up, there is friction. So what we want to do now is actually represent this equation in a block diagram form. So we will have a dv by dt, which is going to be equal to 1 over m times the two terms. On one hand, we have a gravitational pull, G, and on the other hand, we're subtracting from G the frictional force B, which is equal to small b times V. So we can represent this as small b multiplying velocity V. Now we only have to complete this part of the block diagram. We have to relate the rate of change of velocity and the velocity, and we have to think about how do we get velocity from the rate of change of velocity, and the answer is through integration. So if we integrate the rate of change of the velocity, if we feed this through the integrator, then when we integrate the rate of change of the velocity, we will get the velocity itself. That velocity gets fed back and counteracts the gravitational pull. So here we see this intrinsic feedback. As the velocity is building up, it is actually acting in the opposite direction to the cause that's causing its increase initially. Eventually, as the velocity is building up, it will come to the point where the frictional force, small b times v, will be equal to the gravitational pull. And when these two forces are equal, the resultant force is equal to 0. And when the resultant force is equal to 0, the rate of change of the velocity is equal to 0, and therefore velocity doesn't change. This person has reached the terminal speed. So now we're going to look at the electrical system. We're going to look at charging up a capacitor. We have a voltage source, a resistor, and a capacitor in the circuit. Voltage of the voltage source designated Vs, current flowing is I, resistance R, and capacitance C. The voltage across the capacitor, designate Vc. The voltage across the resistor, designate Vr. So we're going to apply Kirchhoff's voltage law to derive the equation, and the equation is Vs equals I times R plus Vc. Okay, what do we do now? Well, we can express I because we know that for a capacitor, C times dVc by dt is equal to I. And we can substitute this expression here to get Vs is equal to C times R times dVc by dt plus Vc. So here we have the equation which is actually relating how the voltage across the capacitor changes as we apply the supply voltage. And we can again, like in the case of the mechanical system, express this in a block diagram form. So what would this look like? So we have Vs there. We have Vc. If we put Vc to that side, it's Vs minus Vc. One over Cr, and we get dVc by dt. And again, surprise, surprise, we have an integrator here, which gets from dVc by dt to Vc. So here we have Vs minus Vc comes in, gets divided by the constant Cr to give us dVc by dt, which then gets integrated to give us Vc. And like in the case of mechanical systems, we have intrinsic feedback in the system, just like in the case of mechanical systems. So far, we have looked at mechanical system and we looked at the capacitor in series with resistor connected to the voltage source. How about this circuit? So we have a resistor, but now we have an inductor. Vs, I, R, and L. Well, in this case, what we have is Vs equals I times R plus VL. But we know for the inductor that VL is equal to L di by dt. Therefore, Vs is equal to L di by dt plus I times R. So this equation here describes how the current changes in this circuit as a result of applying a voltage at the voltage source. Now this equation, Vs equals to L di by dt plus IR, might look somewhat unfamiliar to you. However, you've seen the equation just like this one in the same form, but for a different type of system. So remember this, n times dV by dt plus B times V. This equation was the equation we derived for a man jumping out of the airplane, and this is the equation for a current inside the LR circuit. Now you will notice a huge correspondence between them. In this case, we have Vs, supply voltage. Here we have a force. Here we have inductance. Here we have a mass. Here we have a resistance. Now what's the mechanical equivalent of resistance? Friction. There is friction. And here we have a current, whereas here we have velocity. But the form is exactly the same. The variables have different physical meaning, but the relationship between them is described using exactly the same type of equations, differential equations, and in particular, in this case, first-order differential equations. The reason why we call them first order is because the order of the differentiation in them is first-order differentiation. So here we have two seemingly disparate systems, one is mechanical, one is electrical, but they're actually described using the same equation form. And unsurprisingly, their responses will also look exactly the same when we apply a constant force to the mechanical system or a constant voltage to the electrical system. The profile of the velocity on one hand and the current on the other hand will be exactly the same for both of these systems. The key observation here is that all these transient responses have identical shapes. They may be stretched or compressed in time or in amplitude, but they are all of the same shape. Whilst for many systems these oscillations are non-destructive, in some cases they may be highly unpleasant or even catastrophic. So we need to properly understand transient behavior and formulate it mathematically. Then we may be able to reduce its negative impacts or utilize it to improve the overall system behavior.